Ether is commonly used as an anesthetic drug, where people would go put people to sleep before a surgery procedure. Okay, the old inhalation anesthetic drug is diethyl ether. So put people to sleep, just simple ether. But the drawback of using diethyl ether is side effect, especially when people recover, try to get awake after the surgery. I mean, it involved vomiting, nausea. I mean, it's just quite a lot of it. So diethyl ether was later replaced by all this halogenated ether. Okay, what do this guy do? So all this ether, they put people to sleep by interrupt the communication between the synapses signal. Right, so there's a nerve cell, there's a nerve ending, there's a nerve beginning right here. There's a synaptic gap. That is where two nerve cells communicate. This is in your central nervous system. Okay. All right, so if you look more closely, so there's within the synaptic gap, it's so hard to say, synaptic gap. All right, synaptic gap. There is a chemical communication between two neuron cells, right? So two nerve cells. One of them produce the chemical signal, like we call neurotransmitter. We have like gamma, amino, butyric acid, acetylcholine, oxytocin. You probably have heard some of those. And so they produce it, and they go by to the receptor of the next synaptic cell. Okay, nerve cell basically. So what do those ether do? So they either interrupt this communication by bind to the receptor, so the neurotransmitter cannot bind to it, or block the release of neurotransmitter on the presynaptic cell, the one before, the one about to release the chemical. Okay. All right. Another application, we have crown ethers. So what is crown ether? So let's start with something you're familiar with. When we make a Grignard reagent, we put magnesium in an ether. Could be a diethyl ether, could be a THF, either way, right? The ability to solvate or to stabilize the positive charge of reagent, that's ether. That's what ether can do. So stabilize right there. See that? Now, this stabilization is weak, right? But it's enough to keep Grignard reagent reactive. Okay? So there's an ion-dipole interaction. And we can increase the degree of this interaction by adding, take a look, this guy. Look like a crown, right? So we have 12 crown 4, which means the 12-membered ring. If you count number of angle right here, there are 12 atoms total. 4 of them are oxygen. 15 crown 5, which means there are 15 atoms in this ring, and 5 of them are oxygen. 18, so 18 atoms, 6 of them are oxygen. All right. This guy, you can see that this compound have multiple oxygen in it, so they can solvate, they can stabilize ion better, right? And if you look at the size, so there's a size difference. The small one, so 12 crown 4, can solvate lithium ion well, because it's the size of lithium ion. Sodium ion, which is bigger, we need a bigger crown, bigger compound, basically. So 15 crown 5. Potassium, lower in the periodic table, so the size is bigger, so we need a larger crown, right? So this guy can solvate potassium. What they can do are that in the look at the outside right here. So the inside is hydrophilic, so they love anything polar, so potassium fit well. But the outside is non-polar, which means that the whole thing here is soluble in organic solvents, right? The whole thing is soluble in organic solvent. Inside of course not, right? But inside love polar, but outside love non-polar. That means that here we go. Take a look. Look at the application. Potassium fluoride, right? Fluoride is one of the worst nucleophile ever because too high in electronegativity, right? It doesn't share electrons with anyone. But we can make fluorine reactive. Okay. All right. Look at the overall real quick. So we have 18 crown, 1, 2, 3, 4, 5, 6, 6, right? Ether. All right. Add potassium fluoride. Use benzene as a solvent. Here's the thing, though. Benzene is non-polar. You guys know that. Benzene is totally non-polar, all carbon, right? Potassium fluoride is ionic. This is freaky as polar ever. Potassium fluoride is not soluble in benzene. Of course, it's not. but we can make it soluble by adding this guy, right? So this guy gonna go solvate potassium, pull potassium away from fluorine, and of course it can beat fluorine because there are too many oxygen here, right? Help each other pull potassium. Fluorine gonna become fluoride ion. Potassium gonna be get solvated inside the crown ether, right? These allow potassium ion, which is not soluble in benzene, soluble in benzene, because outside right here hydrophobic is soluble in benzene. This is how we get ionic compound into the let's say it one more time. This is how we get an inorganic compound like metal, right, into non-polar solvent. Totally have different opposite polarity, right? But we can do that by using crown ether. And not only that, the fluorine right here become highly nucleophilic. Take a look at 18 crown ether in crown 6, potassium fluoride and the benzene as a solvent. Fluoride become highly nucleophilic, can attack at that position, just SN2, 92% yield. This is amazing. Fluoride normally never ever do act like a nucleophile. All right. So this is application in organic synthesis. Now in medicine, take a look in medicine. Also a little bit more, So crown ether become soluble in benzene. Yeah, make potassium fluoride soluble in benzene, and fluoride become highly nucleophilic. Okay. This is application in organic chemistry. Now we're going to go to medicine, antibiotics. Right. We use crown ethers as an antibiotic. Any cell, this is a bacterial cell, right? But any cells, if you're familiar with sodium potassium pump, right? So potassium and sodium can go inside and outside of the cell using this pump. Anyway, what I want to say is, so to be for a cell to be able to function, they need to maintain certain concentration inside and outside the cell. All right, and the concentration could be anything. And right now we talk about potassium ion and sodium ion. They need to have some certain concentration inside and a certain concentration outside. Otherwise, cell cannot function and cell dies. Okay, so look at right here. So in sodium, potassium cannot pass through the cell membrane because the hydrophobic nature. Right here, this is all fat right there. Right, so potassium, sodium ion, which have ion, cannot pass through it. But we have something look like similar to crown ether. We call ion. So no, ionophores. That's so hard to say. Ionophores. It's kind of ion, and force mean like hole. So like a hole for ion, basically. So we call ionophores. Ionophores are type of crown ether. That have ability to carry ions and bring the ion inside the cell and disrupt sodium potassium gradient inside the cell. So it looks something like this. Here we go. They can carry a lot of ions actually. So sodium ion can bind here, potassium ion can bind here, sodium ion can bind. There's quite a bit of ions that can be transported from outside inside the cell. So when we put these two let's say nearby a bacterial cell, right? So this guy will carry ions into it and then kind of sneak inside the cell and then add potassium, add to the concentration of potassium ion and sodium ion inside the cell, change the gradient of this ion inside the cell, and then basically break the cell. Okay, so the two main ones that they commonly use, we have nonactin and monensin. I don't know how to say it, but yeah, that's how they do it. All right, that's a good application of ether. Let's move further to how to make an ether.